Welcome to Lyons Township High School AP Physics. Today I got a real short example involving circular motion and a car. So let's say you're driving a car and you are simply driving in a circle, okay, in a flat parking lot, let's say. And question that you might want to ask is, what's the fastest you can go and not skid, okay, in the circle? Okay, so let's say you're given the following things. You are given the radius of the turn, the coefficient of static friction, the coefficient of kinetic friction, and you want to determine what's the max velocity that the car can go without skidding out of the turn. So, first question is, if you're going in a circle at a constant speed, are you accelerating? Yes, you are, okay? As long as any change in velocity over time is acceleration. Acceleration is delta v over t. Well, velocity is speed and direction. If you're changing either your speed or your direction, you are accelerating. So since we're turning and we're going in a circle, we are constantly changing our direction, so we are constantly accelerating. And also you feel it. If you're going in a car and you hit the gas, you feel like you get thrown back. If you're in a car, hit the brakes, you feel like you get thrown forward. Well, if you're in a car and you turn, you feel like you get thrown outward. Now again, all those are actually the opposite directions of the accelerations, but that's the feeling of acceleration when you feel like your body's been thrown some way. So you are accelerating. Now, which force accelerates you? Well, that's usually a pretty easy one to answer. There's only a few forces acting on the car. You've got the ground pushing up on the car. That's the road, the normal force. You've got the car's weight pulling down. But neither of those acts left or right. So we need a force that acts, like let's say you're turning left, we need a force that acts left. What's the only force left between the tires and the road? Well, it's friction. Okay, so friction is what turns your car. And you know that because if there's no friction, aka if you're on, let's say, a really icy road and you try to turn the steering wheel, the car don't turn. So you have to have friction to turn you. Friction does the turning for you. Now, the next question is, which kind of friction is doing that turning, static or kinetic? Well, if your wheels are rolling along the ground, if they're rolling and they're not skidding, then it's actually static friction doing the turning. Because at any moment, the part of the wheel that's touching the ground is not moving relative to the ground. So that's static friction. Now, if you were skidding, like you apply the brakes hard enough where you slide to a stop, well, then that would be kinetic friction. But here we got static friction. So we don't even need this, okay? And we're going to start with a couple sketches. The first is a top view. So there's a top view of the circle. Okay, so here's the circle the car's going in. Here's the top of the car. If there was no friction, let's say the car's going that way, the car would just slide off in a straight line. Okay, so which way does friction have to point to pull the car into a circle? Well, it has to point inward. There has to be an inward force. So friction points inward. Another way to look at that is the car, it's as if it's trying to skid out of the circle, and so the relative motion is out of the circle. Friction opposes relative motion and tries to pull it in. All right, now, the unfortunate part of this diagram is you can't see the other two forces. The other two forces are mg pointing into the board and the normal force, the road pushing up. So we're going to draw a rear view of the car, and then we can get all three of these forces in here. So there's the rear view, there's the tires, there's the driver's head. All right. So now you've got mg acting down, you've got the normal force acting up, and then we'll say you're turning left. That means friction points left. Okay. Now, we're going to find the max velocity in terms of the givens. Now notice there's only really two givens up there. I didn't give you the mass of the car. We'll see if we need it. Okay. So we're going to analyze this using net force equals ma. Now, there are two directions to analyze here. The first one is the vertical direction. Now, the car is not accelerating up, nor is it accelerating down. It's not jumping off the road or crashing through the road. Therefore, we know the net force in the vertical direction is 0, meaning this and this are equal. So I will write that down here as just a reference. We know that Fn is going to equal mg in this special case. Usually in most of our problems, Fn does not equal mg, but here it does because we have nothing else vertically happening. Okay? The direction that we're interested in is the radial direction. Toward the center of the circle is positive, so this way will be positive. Okay? And so we'll put little r's here for this is the radial direction. Well, the only force acting in the radial direction is friction. So force of friction equals m, and then the acceleration, the radial acceleration of anything going in a circle is v squared over r. Force of friction. Now we're going to do a series of substitutions. What's the equation for the force of static friction? Well, it's mu sub s times Fn. So that's going to equal mv squared over r. What's Fn equal? Well, we just got done saying that Fn in this problem, in this special case, equals mg. So I'm going to plug that in. So mu s times mg equals mv squared over r. Aha! What happens in the mass of the car? It drops out. So it doesn't matter if it's a Matchbox car or a Mack truck. All that matters is the radius of the turn and the coefficient of static friction between the tires and the road. That's it. Okay? If you multiply both sides by r and square root, you got your answer. So Vmax is a square root of mu sub s g r. And of course, we could throw values in there, but I'll leave that to you to do. You can pick any values you want. So mu sub s for a regular set of tires is roughly 0.8 or something. G is 9.8, and radius of the turn depends on what turn you want to make. So again, it's same thing we've been doing. You draw an FBD, you establish a positive direction, you write out Newton's second law, you figure out what forces go in the net force. Well, in this case, we only had one. And then you might have to do a few substitutions to get to your final result. So I hope that was helpful, and thank you very much.